Hello everyone, so this video will discuss how pentose and hexose carbohydrates from cyclic structure. Based on the video, it describes hexose and pentose molecules as linear structures. However, it cannot explain a certain number of chemical and physical properties. So I am here to discuss and show about pentose and hexose form cyclic structure. First, let's talk about the unexplained chemical property. Molecules that have a highly reducing aldehyde group are characterized by a very specific reaction called the Schiff reaction. Schiff reaction has a reagent called Schiff reagent that has been first discolored with sulfur dioxide. This Schiff reagent is recolored and turned into pink again. So, if a molecule of aldose is linear, we expect to see one free aldehyde group. And we expect that an aldose will recolor the Schiff reagent. What we observe is that an aldose fails to recolor the Schiff reagent, suggesting that aldehyde group in an aldose is masked inside a cyclic structure. Moving forward about unexplained physical properties. Given the example here, a linear molecule of D-glucose, for example, should exist in one form and have a unique set of physical properties. For example, a unique melting temperature and a unique degree of rotation of polarized light. In fact, when two distinct methods are used to chemically synthesize the glucose, you obtain two forms that differ by their melting temperature. So, 146 degree versus 150 degree, and by rotation of the polarized light, 112 degree and 18 degree. In addition, structural analysis showed that hexose and pentose exist in cyclic structure. In fact, in solution, linear and cyclic structure are in equilibrium. However, linear structure represent only 0.2% of the molecule of sugar in this solution. So, how can we form a cyclic structure? Going back to a very basic chemistry, when an aldehyde reacts with an alcohol, you form an hemicetal. Similarly, when a ketone reacts with an alcohol, you get an hemiketal. Now, in an aldose or ketose, you have an aldehyde or a ketone group, and you also have alcohol function, hydroxyl groups. Therefore, you can have an intramolecule hemicetation or hemiketylation, and that will lead what we call cyclic structure. We start with a linear molecule of glucose and then bend the covalent bonds to bring the hydroxyl group carried by carbon 5 in close proximity to carbon 1 that carries the aldehyde group. This is the aldehyde group, the red arrow there. Now, the formation of hemicetal is possible and it can be formed in two different ways. The hydroxyl group on carbon 5 can attack the carbon 1. Either from the front or from the back, leading to a new asymmetric carbon, a new chiral center. And as a consequence, two isomers form called alpha and beta. Let us consider for a few minutes some nomenclature. The carbon 1 that is involved in this cyclization is called the anomeric carbon in the cyclic structure. In the alpha isomer, the hydroxyl group carried by carbon 1 and carbon 6 are in opposite direction, which means that in our representation, the hydroxyl group carried by carbon 1 is below the plane formed by the ring structure. In the beta isomer, the hydroxyl group carried by carbon 1 and the carbon 6 are in the same direction, which means in our representation of the beta isomer, the hydroxyl group is above the plane formed by the ring structure. Now we can go back to this difference in the physical properties to understand more. Because one method of synthesis leads to the alpha form of the glucose, and the other method leads to the beta form of the glucose. And these two isomers have slightly different physical properties. So, with that ketose can form a cyclic molecule since they can form an hemiketal. So, for example, in a pentose and carbon 5, or the hydroxyl group carried by the carbon 5, can react with the carbon 2 that carries the ketone group to form a cyclic structure. In this case, the carbon 2 will be defined as the anomeric carbon. Now, you can form a large variety of cyclic structures. For example, you can form a large variety of cyclic structures. For example, you can form hexoaldose, pentoaldose, hexoketose, or pentoketose. So, all of these molecules, all of these hexose and pentose, whether they are aldose or ketose, can form a cyclic structure. Now, if we look at the structure of the ring, we can see that we have two different types. One that contains 6 atoms, 5 carbon, and 1 oxygen. And this ring resembled a structure of a molecule called pyran. And then we can have a ring that contains 5 atoms, 4 carbons, and 1 oxygen. And the structure resembles the structure of what we called furan. So it can form a new nomenclature. For example, alpha-D-glucose has a ring that resembles pyran and we can call it alpha-D-glucopyranose or ribose beta-D ribose has a structure that resembles a furan, and we can call it beta D ribofuranose. Remember that nomenclature is more informative since it takes into account the structure of the ring that is found, and that is important when the same molecule can form two different ring structure.